Welcome to today's paper reading. Today's paper is titled, Scalable MatMul-free Language Modeling. This paper, titled Scalable MatMul-free Language Modeling, was authored by Rui-Jie and colleagues from the University of California, Santa Cruz, and other institutions. It is currently under review for publication. In this work, the authors address the computational burden of matrix multiplication, MatMul, in large language models, LLMs. As LLMs scale, the cost of MatMul operations increases, but the authors demonstrate that these operations can be entirely eliminated without compromising performance. Their experiments show that their MatMul-free models perform comparably to state-of-the-art transformers, even at billion-parameter scales, while significantly reducing memory usage during inference. The authors also implement a GPU-efficient model that reduces training memory by up to 61% and can decrease inference memory by more than 10 times compared to unoptimized models. To further enhance efficiency, they develop a custom hardware solution on an FPGA, achieving processing at 13W beyond human-readable throughput, which brings LLMs closer to brain-like efficiency. This research not only showcases the potential for simplifying LLMs, but also suggests the types of operations future accelerators should optimize for in the next generation of lightweight LLMs. Matrix multiplication, MatMul, is a fundamental operation in neural networks, particularly in dense layers, convolutions, and self-attention mechanisms. The prevalence of MatMul is largely due to the optimization of graphics processing units, GPUs, for these operations, which can be efficiently parallelized and accelerated using frameworks like CUDA and libraries such as CuBLAS. However, despite its efficiency, MatMul operations account for a significant portion of the computational expense in neural networks, often consuming the majority of execution time and memory access during both training and inference phases. To address this, several strategies have been proposed to replace MatMul with simpler operations. One approach involves substituting MatMul with elementary operations, such as the use of signed addition in ADNet for convolutional neural networks, CNNs. Another approach employs binary or ternary quantization, simplifying MatMul to operations where values are either flipped or zeroed out before accumulation. These methods can be applied to either activations or weights, and in some cases, they are combined to further reduce computational complexity. In the realm of language models, the focus has been on quantization techniques. Early efforts involved reducing a ternary BER to a binarized model, achieving significant accuracy on GLUE benchmarks. More recent approaches include incremental quantization, progressively reducing model precision, and quantization-aware training for models with low bit weights. Moving to MatMul-free transformers, significant progress has been made with SPICformer, integrating SNNs with transformers, and developing spike-driven transformers. These have shown success in vision tasks and language understanding, such as with spiking BERT and SpikeBERT. Challenges remain in scaling these models, particularly with binarized activations. Innovations like binary vision transformers and piecewise affine approximations for multiplication-free training continue to push the boundaries in this field. The method section introduces a novel approach to language modeling by eliminating matrix multiplication, MatMul, operations. This is achieved through the use of MatMul-free dense layers with ternary weights, which constrain the weights to the set -1, 0, +1. This transformation replaces MatMul operations with addition and negation, significantly reducing computational cost and memory utilization. To further optimize hardware efficiency, the authors propose a fused bilinear layer that combines RMS norm and bilinear operations, minimizing data movement between high-bandwidth memory, HBM, and shared memory, SRAM. The MatMul-free language model architecture includes a token mixer based on the MatMul-free linear gated recurrent unit, MLGRU, and a channel mixer employing the gated linear unit, GLU, with bit linear layers. This architecture relies solely on addition and element-wise products, maintaining the expressiveness of the network while enhancing computational efficiency. Figure 1 illustrates the training loss progression over steps for two models, the MatMul-free Transformer ++ and our proposed method, both at the 370M parameter scale. the MatMul-free Transformer++ exhibits a failure to converge, as indicated by its fluctuating and non-decreasing loss curve. In stark contrast, our proposed method demonstrates successful convergence, with a clear downward trend in the training loss. This comparison highlights the effectiveness of our method in achieving convergence under a MatMul-free setting, which is crucial for the efficient training of large language models. Figure 2 provides an overview of the MatMul-free language model (LLM) architecture. It contrasts the sequence of operations in vanilla self-attention with those in the MatMul-free token mixer and ternary accumulations. The MatMul-free LM incorporates a MatMul-free token mixer (MLGRU) and a MatMul-free channel mixer (MatMul-free GLU) to preserve the transformer-like structure while significantly lowering computational costs through the use of ternary accumulations. Figure 3 presents a comparison of the scaling laws between MatMul-free language models (LM) and Transformer++ models, visualized through their respective loss curves. The red lines signify the loss trajectories of the MatMul-free LM, which employs ternary parameters and BF16 activations. Conversely, the blue lines represent the losses of the Transformer++ models, which utilize BF16 parameters and activations. Notably, the star symbolizes the intersection point where the scaling law projections for both model types converge. This figure highlights the efficiency and performance differences between the two model architectures as they scale. In this section, we focus on testing the MatMul-free LM on moderate-scale language modeling tasks. We compare two variants of our MatMul-free LM against the reproduced advanced transformer architecture, Transformer++, across three model sizes, 370M, 1.3B, and 2.7B parameters. All models are pre-trained on the SlimPajama dataset, with the 370M model trained on 15 billion tokens, and the 1.3B and 2.7B models trained on 100 billion tokens each. The training was conducted using 8 NVIDIA H100 GPUs, with durations of approximately 5 hours for the 370M model, 84 hours for the 1.3B model, and 173 hours for the 2.7B model. We also evaluate the scaling law, finding that the MatMul-free LM exhibits a steeper descent compared to Transformer++, suggesting greater efficiency in leveraging additional compute resources. The scaling curves are projected to intersect at approximately 10 to the power of 23 flops, indicating potential for superior performance when scaled up. Figure 4 provides a comprehensive analysis of the performance and configuration differences among various models. Subfigures A and B detail the training performance of vanilla bitlinear versus fused bitlinear, focusing on time and memory consumption relative to batch size. Subfigure C illustrates how the learning rate impacts training loss for the MatMul-free LM. Finally, subfigure D contrasts the inference memory consumption and latency between the MatMul-free LM and Transformer++ across different model sizes, highlighting the efficiency gains of the MatMul-free LM. Table 1 presents the zero-shot accuracy of MatMul-free LM and Transformer++ across various benchmark datasets. The comparison is made at three different model sizes, 370M, 1.3B, and 2.7B parameters. Each model size is evaluated with corresponding training tokens and architectural configurations. The table highlights the performance differences between MatMul-free RWKV4 and Transformer++ in terms of accuracy across different datasets, providing insights into the efficiency and effectiveness of each model architecture. The FPGA implementation of the MatMul-free token generation core includes 4 functional units: row-wise operation, root mean square, load store, and ternary matrix multiplication. A custom assembler was developed to convert assembly files into an instruction ROM. The register router manages instruction delegation to available registers. Performance metrics show a forward pass time of 43 milliseconds at a clock rate of 60 MHz, with extremely low dynamic power. Future optimizations include parallelizing the TMATML functional unit and implementing caching improvements to mitigate DDR4 channel contention. Figure 5 illustrates the RTL implementation for running MatMul-free token generation. The design includes 4 functional units: row-wise operation, root mean square, load store, and ternary matrix multiplication, which allow for simple out-of-order execution. A custom assembler is used to convert assembly files into an instruction ROM, and the register file consists of 8 registers, each storing one vector in a separate SRAM array. This setup highlights the efficiency and precision of the MatMul-free LM implementation on custom hardware. Table 2 presents the resource utilization and performance metrics of the MatMul-free token generation FPGA core. The data indicates that the ternary matrix multiplication operation significantly impacts latency. The core's resource utilization is primarily limited by adaptive logic modules, ALMs, not on-chip memory. Future optimizations aim to improve the DDR interface and parallelize the TMATML functional unit, projecting a 64x speedup. This table is crucial for understanding the current bottlenecks and potential improvements in the core's performance. Table 3 presents the FPGA performance metrics across different embedding dimensions D. The runtime, projected runtime with bursting, power consumption, ALM utilization, and clock rate are detailed for embedding dimensions of 512, 1024, and 2048. This table highlights how these metrics change with increasing embedding dimensions, providing insights into the efficiency and resource usage of the FPGA core under various configurations. In this study, the authors have successfully demonstrated the feasibility and effectiveness of the first scalable MatMul-free language model. This work challenges the conventional belief that MatMul operations are essential for high-performing language models, opening new avenues for more efficient and hardware-friendly architectures. The model achieves performance comparable to state-of-the-art transformers without the need for MatMul operations, thanks to an optimized implementation that significantly improves both training and inference efficiency, reducing memory usage and latency. As the demand for deploying language models on various platforms increases, MatMul-free language models offer a promising direction for creating models that are both effective and resource efficient. However, the study notes a limitation. The MatMul-free LM has not been tested on extremely large-scale models due to computational constraints. This research serves as a call to action for institutions and organizations with the resources to build the largest language models to invest in accelerating lightweight models. By prioritizing the development and deployment of MatMul-free architectures, the future of large language models will become more accessible, efficient, and sustainable. Thank you for watching.